Hello everyone and welcome to this video. Today we're gonna cover the triple integrals in cylindrical and spherical coordinates. And so as you can see, we have here the cylindrical coordinates of a point in the space, which are r, theta, and z. Now as you can see, we have the point r, theta, and z, which is p, r, theta, and z. We have also here, so theta is the angle from the x-axis. This is our x-axis. And theta is the angle in the xy plane from the x-axis. And now we do have r. So r is basically the distance from the origin up to the point, of course, in the xy plane. So the projection of the point is in the xy plane is gonna be this point. So it's gonna be just r theta 0. This is the projection in the xy plane, and we take r to be the distance from 0 up to that projection, and theta is basically the angle from the x-axis up to r in the xy plane. And then we have z is basically the height of that angle, and that's basically how we express the cylindrical coordinates of a point in the space. And so we have here our definition. So cylindrical coordinates represent a point P in a sphere by order triples r, theta, and z, in which r and theta are polar coordinates for the vertical projection of P on the xy plane. So as we said, the vertical projection of P, which is this one, this point, basically on the xy plane, so these represent r and theta, and z is the rectangular vertical coordinate. So the distance that we need to go up in this axis. And now here we have some equations relating the rectangular xyz and cylindrical coordinates, and these are basically summarized here. They are very similar to the ones that we have in polar coordinates, okay, but we have the addition of z equals z. So in polar we have x equals r cosine theta. That's basically in polar, which is the same as cylindrical coordinates. And we have also y equals r sine theta. We used to have r squared equals x squared plus y squared. That's a formula. And we also used to have tan theta equals y over x. And now we just have the addition of z equal to z. And that's basically the cylindrical coordinates. And so let's have some examples. So he wants us to express the point 2 root 2 in cylindrical coordinates. So here we have x, y, z. Now we want r, theta, and z. And so we're gonna convert r into x. Sorry, we're gonna convert the xy into r, and we're gonna convert it also to theta. So now to get r, we're gonna just use the formula r squared equals x squared plus y squared. And so r equals the square root of 2 squared plus square root of 2 all squared. And that's basically going to give us square root of 4 plus 2, which is 6. So square root of 6. Now this is r. And for theta we can use the tan. So tan theta equals y over x. And theta is tan inverse of y over x. Give me a second, let me get out my calculator to find this. Now tan theta, so we're gonna evaluate tan inverse of y. Y is basically the square root of 2 over 2. Now we go tan inverse of the square root of 2 over 2, which is gonna give us basically, in radians, is gonna give us an angle, or let's take it in degrees, okay? So in degrees, it's gonna give us an angle of 35.26 degrees. And now z remains the same, and so our points is basically square root of 6, 35.26 degrees, and minus 1. And this is our point. Now we converted this from Cartesian coordinates into, or rectangular coordinates into cylindrical coordinates. Now let's take example 2. So he wants us to express this point in cylindrical coordinates into rectangular coordinates. So we do the opposite. So we have r equals -2, and we have theta equals 2 pi over 3. So he's expressing it in radians, so we can use radians now. And z equals to 3. Now will remain the same for rectangular and cylindrical coordinates. Now we want to find x and y, so we can use this formula: x equals r cosine theta, and so x and y equals r sine theta, and basically r is -2, and then cosine of 2 pi over 3, so 2 pi over 3, and this you can, so you'll get -2 times, so basically cosine of 2 pi over 3 is just 1. Okay, so yeah, no, actually cosine of 2 pi over 3 is -1 over 2, multiplied by 2 is gonna be 1, and for the y we're gonna use sine of the angle, and we're gonna get, so here we have x equals to -2 times -1 over 2, and we're gonna have y equals -2 times √3 over 2, and so -2 times √3 over 2 is gonna give us -√3, and now we have all of the required coordinates. So x is 1, y is -√3, and z is a 3. Now this is the point in rectangular coordinates. Now go to example 3. We need to find the equation in rectangular coordinates. Now this is our equation in cylindrical. Now we want to convert it to rectangular. So basically for r squared, we're going to use x squared plus y squared, this formula. And for cosine 2 theta, so basically cosine 2 theta, this has this has an identity. So cosine of 2 theta. Let's Google this formula. Okay, so cosine 2 theta, that's basically what you do when you want to find any formula. You just go and Google it, basically. And now we do have, so we get something like, yeah, so we get something like cosine. We can use, so there are multiple formulas for this. So we're going to use cosine 2 squared theta -1. And now, okay, let's just do it like this first. We're gonna convert it like this, and now cosine theta is basically using x equals r cosine theta, and squaring both sides, we're gonna get x squared equals r squared cosine squared theta. Now we can use this cosine squared theta in order to convert to x, and so cosine squared theta is just x squared over r squared. Okay, so, and now we can substitute this. Now here we have x squared plus y squared equals 2 times x squared over r squared, and r squared in polar is just x squared plus y squared, and this is -1. And now this is our formula. Now we can try to simplify this, try to, make it simpler. So we're gonna do something like x squared plus y squared equals to 2x squared over minus x squared minus y squared all over x squared plus y squared. And now we're gonna have just basically this. So x squared plus y squared all squared equal to x squared minus y squared. And that's basically the simplest thing we can get here. We can try to expand and get all of the, the other things, but that's basically enough. We can expand this and get something like x to the 4 plus 2 x squared y squared plus y to the 4. We're gonna make it equal to x squared minus y squared, and that's basically our equation in rectangular coordinates. Now let's take this. Let's look at constant coordinate equations. Okay, so there are constant coordinate equations in cylindrical coordinates. can yield to cylinders and planes. So in cylindrical coordinates, we can get either a cylinder or a plane when we have a constant coordinate. So we have one coordinate constant, and like for example z, and take the rest to be here variable. So r and theta, we take them as variable, and we take z as constant. So these are gonna yield rectangles and sorry planes and cylinders. So if we make theta, let it be constant. Okay, so we have here, let's say r theta z, and theta, let's say, is 0, for example. So in our example here is 0. So we call it theta naught. Okay, so when we have theta is 0, we're gonna yield a plane. And why is that? So basically theta is constant and r is changing, and so we're gonna have r from here going all the way to infinity and minus infinity, and we're gonna have z that's varying in this direction, and so we're gonna get a plane. So this yields a horizontal plane. Now if we take for example z and let it equal to a constant, so we're gonna have r theta and then z naught. So this is gonna yield us also a plane, as you can see here. In the red, this plane is gonna be the yield of leaving z constant. Why is that? Because basically if you see, we're gonna have z constant, so it's not gonna change, but we're gonna have r, which is in this direction, changing, and also we're gonna have theta changing here. So this is theta, so we're gonna have multiple lines all adding up to a vertical, or say, actually this is a vertical plane. Okay, vertical. The orientation is vertical, and it's gonna yield us here, when we let z equal 0, a horizontal plane. So all these lines just add up to make us a plane. So these lines, and also different lengths, so different r's, okay, and different thetas. Now we're gonna have infinitely many thetas and infinitely many r's, and so it's gonna yield us at the end this plane in red, and so we're gonna have a horizontal plane for our for our z naught equal to constant. Now if we take r constant, okay, and we let theta and z vary, and so we let r equals r naught, so we have r naught theta z naught. Now this is gonna yield us a cylinder. And why is that? Basically we have a specific r that we are dealing with, and we have theta that's varying, so this is theta, so we'll have different different lines with r equal to r naught, so this r has a constant value, but also we have a varying z, so we're gonna have also the same thing here. We're gonna have different lines with the same r and with different thetas and with a different z, and so this is gonna yield us at the end like a stack of circles. Yeah, so a stack of circles, as you can see. So this is the circle. A stack of circles is gonna yield us basically what? A cylinder. So it's gonna yield us a cylinder. So basically that's the effect of making some coordinates constants. So now let's try to move on. Okay. Okay. And so now we can see this. Now this is basically also cylindrical coordinates. So if we let the volume of the wedge approximated by delta z r delta r theta. So in cylindrical coordinates, the volume of the wedge is approximated by the product delta v equals r delta z delta r delta theta delta z, which is basically similar to our delta a, which we have in cylindrical coordinates, but in 2D or in a triple integral, we're gonna have r delta theta. Just the difference is that we're gonna add here delta z. That's basically the approximation of such a wedge that we have. So that's a wedge. And so basically when we multiply all of these, the delta r delta theta, and then we multiply it by delta r and then by delta z, is gonna give us this specific volume. So r delta theta. So this is r, this is delta theta, and this is the length r. So multiply r delta theta like this. We have also delta r, delta z, and r delta theta. Yeah. So it's basically like this. Gonna have this. We're gonna approximate this by r theta. This is the length of this arc. Multiply it by delta r, which is basically this length. Okay, so sorry, that's r delta theta. Okay, so that's the length of the arc, and that is our, delta r here. And then we just gonna multiply it, this is in 2D, and it's just gonna be multiplied by the height delta z, and it's gonna give us the approximation of the volume. And now this will lead us this triple integral, which is in terms of cylindrical coordinates, it's gonna be a bit different, but it's not very different from our regular triple integrals. Now, let's make this more visible to you. Now, the triple integral of f of x, y, z dv equals the triple integral of a to beta h1 theta h2 theta, now function of theta, and then we're gonna have u1 of r cosine theta r sine theta, so function of r and theta, and u2 r cosine theta and r sine theta. And you have r f of r cosine theta, r sine theta, z dz, dr d theta. And that's basically the triple integral in of course 3D in cylindrical coordinates. So also you don't forget to add the r, make sure that all the x's and y's also get converted over the cylindrical coordinates. So you're gonna add the r in the x's and y's, and also you're gonna add it in the the ends, the boundaries of the integral. And so that's basically our integral. Okay, and so if we like zoom in a little bit, you can see it better. Okay, that's the integral. Now let's try to solve. So let's just show you. Okay, let's show you something here. Okay, so let's now try to show you here this picture. So we have the Cartesian coordinates, so x squared plus y minus 1 all squared equals 1. Now this is the lower circle. We have in polar r equals 2 sine theta. Okay, and at the top here we have also z equals x squared plus y squared. Now this is the upper surface. Okay, this is a hyperboloid or paraboloid. Okay, paraboloid, and then we're gonna have also z equals to r squared. Okay, and that's in cylindrical. We're gonna just equate these, and that's our upper surface, and that's, we can say, our constraint in Cartesian and polar. So it's just finding the limits of integration for evaluating integral in cylindrical coordinates. So we need to be able to draw this and understand and be able to convert also to polar and cylindrical coordinates in order to be able to integrate. And so that's the shape that we can integrate now. And let's see also example 2 now. Here we have first z equals x squared plus y squared. This is the upper surface. This is the paraboloid. Okay, also a paraboloid. And now we have the lower surface is x squared plus y squared. That's like the constraint. And then it looks like it's empty from the inside, and then the volume is just the outer part of this paraboloid. And we can also find the centroid. Okay, interesting. So we're gonna have an example in which we find the centroid. So the centroid is like somewhere here. Interesting. Now let's solve these examples. Okay, let's have these, the definition, and let's solve this. Now let's take this to our board and try to solve this. So we're gonna add a new photo now like this. We're gonna have it like this, and that's our basically example. Now let's go to example one. So he wants us to evaluate the integral, the triple integral e y dv in the region that lies below the plane. So we have a plane equals z equals x plus 2, and above the xy plane. Okay, so we want the region below this and above the xy plane. Okay, and between the cylinders, x squared plus y squared equals 1, and x squared plus y squared equal to 2, to 4. That's basically, let's try to draw this. Now, gonna have something like, okay, so we're gonna want to find first the intersections here. So z minus x equals 2. So we're gonna try to find the intersection. Now, how are we going to do that? So let's let z equal to 0. So x, y, and z. Now, when z is equal to 0, we're gonna have the function x equals negative 2. That's when z equals 0. So when z equals 0, we're gonna have x equals to negative 2. So somewhere here, that's our line. Okay, x equals to negative 2. Now, if you have z equal to 1, let's say, okay, so we go up, we're gonna have yeah, 1 minus 2, so x equals to negative 2, so we're gonna have somewhere something like this. So our function, and basically it's gonna be a plane like this, so it's going all the way like this. Okay, so yeah, if you look at it from this side, from the xz plane, let's say this is our xz plane, x and z plane. Now we're gonna see something like this. We're gonna see this line, which is basically our function. So z equals x plus 2. So the intersection here is 2, and this is minus 2. And that's what we're gonna find from the side. I wish I could have drawn it better, but this is basically what we're gonna get. And then for that, it's just a plane that's extended into the paper and out of the paper. So I hope you can imagine it. Now we want the region. So this region. So this is basically like a tetrahedron. It's like a tetrahedron. We want this region, and we want to find the volume. Okay, so let's try to do that. And also we're gonna have a cylinder. And so a cylinder, we're gonna have, yeah, and the cylinder, yeah, x squared plus y squared equals 1, and x squared plus y squared equals to 4. now. So in the XY plane, we're gonna have, let's try to do it again this time. So do something like this. We do this, and then try to draw it like this. Now this is our plane, and then we're gonna have also a cylinder. It's gonna be like this. It goes all the way here, and also we're gonna have a smaller one, smaller cylinder. I guess. So these are our two cylinders, and we want the volume here in between those, below this plane, above the XY plane, and let's say this is Y, and also between these two cylinders. Interesting. Okay, so we can evaluate this. So how can we do this? This now take our integral, evaluate of course y, then we're gonna need dy dz dx. Okay. Now for y, we want to have the two variables. It's gonna be interesting. So we want to evaluate this. Let's try to see how can we do that. Just check this. Taking the example. Trying to find this specific example. Okay, so basically, since it's hard to visualize this, I'll try to do something about this. Okay, so as for the y, we're gonna require a z here. Basically, not sure how can we get the z here. Okay, we want to have y, so function of y. Okay, maybe you can do something like r squared equals 1 if we convert to our cylindrical coordinates. And so here z is gonna equal to r cosine theta plus 2. So our function. Now of course we're gonna have x equals 0, y equals 0. So we're gonna start with y equals 0 and we're gonna go to up to a different level, and so yeah. So basically we do not need to do that. We can just basically do convert y into sine theta into cylindrical, because we are discussing cylindrical, so dr d theta dz. Now for the r, here we have r equals 1, r equals 2. So the r is gonna go basically from 1 to 2. Now for the theta, we're gonna have theta go from, so we're gonna include also this volume since the plane extends to that. Okay. And so it's gonna be something, the volume is gonna be something like this. Let's just show you how it's gonna be. It's gonna be something like this. Okay, it's gonna stop here and it's gonna continue. And then it's gonna go all the way here and here. Okay, so this is our volume. Now this is gonna be a solid. Okay, is gonna revolve all the way like this. So you're gonna imagine a cylinder. So that's basically a cylinder. So you're gonna imagine it's revolving like this, and this is a section. The one that I'm drawing is just a section. And you're gonna imagine it also go this way, like that. And that's basically how it's gonna be. So like this, it's gonna go like this, and now it's basically our cylinder. Okay, goes like this, goes like this, and you're gonna imagine this being filled like this. Okay, something like this, something like this. Now this cylinder is filled, so we're gonna have some hidden light here. Okay, and now yeah, so it's filled like this. Now that's basically our volume. Now this area is filled and what's emptied from the inside. So we can draw some hidden lines like this. Can draw some hidden lines here, hidden lines here. It's basically like emptied from the inside and filled at this area. And that's basically the volume. Okay, so that's the volume that we are trying to find the area for. It's a bit challenging to try to draw these, but yeah, that's basically the volume. And then, so we want to find now d theta. Okay, now from which angle we're gonna just say 0 to 2 pi. And for the z, is gonna go from z equal to 0 up to z equal to, okay, yeah, so from 0 up to, now, okay, oh, that's a big O. So x squared polar, we're gonna start with u. Okay, so we're gonna start with z. Z, dz, dr, d theta. So let's go dz, dr, d theta. That's important. We start with z. So dz, dr, d theta. Now I'm learning with you at the same time, so bear with me. So z is gonna go basically from 0 up to z equals r cosine theta plus 2. So we're gonna have r cosine theta plus 2. Now this is for the z. Now for the r, we're gonna go from 1 to 2. That's our r. And for our theta, we're gonna go from 0 to 2 pi. And that's basically the volume. Do we need to find the volume? Do we need to evaluate the integral? Yes, we need to evaluate the integral. I don't think it's gonna be that hard, so let's try to do that. Maybe we're gonna need some trigonometric substitution or stuff like that. Use trigonometry, I hope not. Plus 2. Now this is gonna be r squared sine theta dz dr d theta. So 1, 2, 0 to 2 pi. Yeah. And now we're gonna integrate with respect to z, so it's basically two integrals, and then z or r squared sine theta, and then z squared over 2, evaluated from 0 to r cosine theta plus 2, dr d theta, that's our z. Now let's try to, from 1 to r, 1 to, this is r here, 1 to 2, 1 to 2, 0 to 2 pi. Now this, so we have this. Now r squared sine theta, double integral of r cosine theta plus 2 minus 0 is 0, so dr d theta. Now how to evaluate this? Well, basically with respect to r, we're gonna take all the thetas as constants, so 1, 2, 0, 2 pi. So we're gonna have r to the 3 sine theta cosine theta. We can simplify this using the cosine 2 or sine 2 theta identity. We're gonna do it now. Just a minute, bear with me. So, and then plus 2r squared sine theta, dr d theta. Go the integral here, okay. And then now we're gonna integrate with respect to r, which is gonna be basically this. R to the 4 over 4. Let's basically do, and then we multiply by 1 over 2 sine 2 theta. Okay, now plus 2 over 3 r to the 3 sine of theta d theta. So of course it's evaluated from 1 to 2, 0 to 2 pi. And now let's evaluate this from 0 to 1. So we're gonna have first 2 to the 4. We have 16 over 4, which is 4, multiplied by 1 over 2, which is 2. So 2 sine of 2 theta, 0 to 2 pi, plus 2 over 3. So 2 to the 3 is just 8. 8 times 2 over 3 is going to give us 16 over 3. We have 16 over 3 sine theta. Now all of this minus, so we're going to have 1 over 4 times 1 over 2, 1 over 8 sine of 2 theta plus 2 over 3 sine of theta. And all of this d theta. Now we can simplify before trying to integrate, so we can do 2 minus 1 over 8 is going to be 15 over 8 sine of 2 theta. 16 over 3 plus 2 over 3 is going to be plus 6. Okay, actually it's minus. So we're going to have plus 14 over 3. Okay, so 14 over 3 sine theta. Now that's very not hard to do. So we're gonna integrate, we're gonna have, now integrating sine 2 theta is gonna be 15, so 15 over 8, and then minus 1 over 2 cosine of 2 theta. Now, if we try to differentiate this to check, so we're gonna have minus 1 over 2 sine 2 theta, and using a chain we're gonna have 2, so we're gonna get sine of 2 theta, so that's correct. Now we're gonna add to it plus 14 over 3 or minus cosine theta. So minus cosine is gonna be just sine, and evaluated from 0 to 2 pi. Now this is gonna yield us, of course here we can simplify, minus 15 over 16. Minus 15 over 16. Okay, so 8 times 2 is minus 15 over 16. Now let's evaluate this. So minus 15 over 16 cosine of 2 times 2 pi is just minus 15 over 16. And then minus cosine of 2 pi is just basically the same thing. So it's gonna be 14 over 3. And then cosine of 0 is also 1. And so we're gonna have this minus 15 over 16 minus 14 over 3. Now what is this? Cosine of 0 is 1. Well, that's interesting. It's really interesting. Did we do a mistake here? Well, we could be. We could have done a mistake. Yes. Okay, so I know exactly what happened. So here, here we should have squared. Okay, and then we have 1 over 2 here. And now we need to repeat this. And I'm not going to do that. Okay, so basically this is gonna just be, let's just simplify how it's gonna be. It's gonna look. Now, so this is what we did is wrong just because of the squared here. I know some of you were screaming, you forgot the squared. Okay, and so I'm sorry for that. So sine of theta let's fix it. So r squared cosine squared theta plus 2 times 2r cosine theta, so 4r cosine theta. Now this makes more sense. Okay, plus 4 d theta. Now this is gonna be a bit more complicated because we're gonna use trigonometry. Okay, or actually we can use substitution for the first part, and then the second part we use the sine 2 theta identity. And so if we continue with this, we're gonna just basically get 1 over 2, 0 to 2 pi, 1 to 2, and then r to the 4 sine theta cosine square theta. Now for this we use substitution. For the other part we just have 4r to the 3 sine cosine, so yeah, sine theta cosine theta plus 4 r squared sine theta d theta. Now basically you can evaluate this. It's now easier to do. Okay, and so this is basically becomes 1 over 2 the integral 0 to 2 pi 2 1 r to the 4 sine theta cosine squared theta plus 2 r to the 3 sine of 2 theta plus 4 r squared sine of theta d theta. Now this is going to be equal to 1 over 2 the integral of 1 to 2 0 to 2 pi, and now we do have, okay, so now we can evaluate this with respect to r. So we have r to the 5 over 5 sine theta cosine theta. Okay, so let's evaluate it. So 2 to the 5 is just 32. So 32 sine theta cosine theta squared plus 2 to the 3 is just 8 times 2, so 16 sine of 2 theta, and then plus 4 times 4, 16 sine of theta. Okay, this is for first part, and then we're gonna have minus, we're gonna have sine theta cosine square theta plus 2 sine 2 theta plus 4 sine theta. All of this d theta, now we can simplify this. So 1 over 2, the integral from 0 to 2 pi, and we're gonna get 32 over 5 minus 1. We're gonna get 27 over 5 sine theta cosine square theta. And we're gonna get also 16 plus 2, which is plus 18 sine of 2 theta. And then 4 plus 16 plus 20 sine of theta. Now that's pretty much very easy to evaluate. Now for let's break this integral. So we're gonna have 1 over 2, so 27 over 10 from 0 to 2 pi of sine theta cosine square theta d theta. Now I separated this for a reason. I'll show you why. Now we can just do 1 over 2 and leave this as sine of 2 theta plus 20 sine of theta d theta. Okay, and now for this we can let u equals cosine theta, so du equals minus sine of theta d theta, which is basically what we have here. So we're gonna have my 27 over 10 integral from 0 to 2 pi, and then we're gonna have, yeah, so we're gonna have u squared du, and we're gonna have it in minus sign, so we're gonna take this minus sign and take it to this side. So we're gonna have minus, the minus sign is gonna go out, okay, and then we just integrate this, and now for this is gonna be just 1 over 2 times 18 from 0 to 2 pi, 18 of minus 1 over 2 cosine of 2 theta. Okay, so sine 2 theta, 1 over 2, that's basically it, plus or minus 20 cosine of theta from 0 to 2 pi. Now this looks like a 0. I can sense that this is gonna be 0. Okay, this part. But let's see. Let's see. Now this can just integrate, so minus 27 over 16 times, so u to the 3 over 3. Okay, and for u, we're just gonna get cosine back. So we're gonna cosine to the 3 theta from 0 to 2 pi. And then for this, let's try to evaluate. So at 2 pi, this is gonna be 1. So we're gonna have 18. So minus 18 over 2, which is 9. So minus 9. Minus 9. Okay, minus. This is gonna be minus 20. Minus. Then at 0, we're gonna have also minus 9. Since cosine 2 theta at 0 is just 1. And minus 20. So it's gonna be, this whole thing is gonna be 0. And now our hopes are gonna be here. And so I hope this doesn't happen to be also 0, since I will need to go back and try to understand what the what happens. So we have cosine all to the 3 over 2 pi, 2 pi minus over 3, of course. Cosine 3 of 2 pi over 3 of 0. Now, cosine of 2 pi all to the 3 is 1, and cosine of 0 is 1, so 1 minus 1, we do have an issue here. I think we do have an issue here. So we had the squared, z squared over 2. Actually, we should not have z as z squared over 2, we should have only z. So I had it right at the beginning. Only z from 0 to r theta plus 2. So actually I had it right in the beginning. But it seems like we're not getting the answer, the exact answer, for some reason. So when you integrate, you get cosine 2 theta. That's how we integrate the sine, right? Yes, that's how we integrate it. So we get this, which is of 0. Which is weird, the volume is not 0 here. Maybe I should change the limits for our theta. So if we change the limits for theta, we take it from 0 to pi, and then we take it, from 0 to pi, and maybe multiply it by 2. So if we take from 0 to pi, we're gonna cover only 1/2 of it, okay? So we're gonna cover something like, yes, on the xy plane, we're gonna have these two circles, okay? So it should go from 0 to 2 pi, but let's now try to do this instead. So pi from 0 to pi, and then we go pi 2 times, and then, yeah. So it's gonna be here 0, only 0, and then we're gonna have pi, and we're gonna continue with pi, okay. Gonna go all the way and try to substitute now. Now if we substitute from 0 to pi, okay, and we already multiplied by 2, but 1 over 2 here cancelled. Or actually, we don't have 1 over 2. It's just 2. Just 2 here. Yeah, so 2 multiply by 2, multiply by 2, multiply by 2, 2, 2, and then here, okay. And so here we go with pi. So minus 15 over 16 cosine of 2 times pi. It's gonna give us 1. But for cosine of pi is just minus 1. So now we're gonna get here plus, a plus sign. For this we're gonna get just negative 15 over 16, okay. Yeah, so that's for the pi, and then for the 0, cosine of 0 is just 1. And so we're gonna have a minus sign here, and we're gonna have a minus sign. Now this cancels with this, and we got just 14 over 3, and of course multiplied by 2, times 2, which gives us the volume of 28 over 3. And that's basically the volume. So we needed to just break down this integral, since for some reason it doesn't allow to have it from 0 to pi. You can just, and we have a symmetry. It's important to note that we have a symmetry over the x-axis here. Okay, yes, it might look as it's symmetrical over here over all axes, but here if we look at it from the z-plane or the z-axis, we're gonna see that there is only symmetry in the x-plane. So the whole solid is symmetrical over the x-axis, and so that's why we cannot do it over, like for example, from pi over 2 to 3 pi over 2. We cannot do that. It's gonna give us a volume for a different solid, and that's not really what we want. It's gonna give us a volume of a solid that looks something like this. Just a weird solid. We're gonna get this shape. So, and we don't want that, of course. So it's gonna be like this. It's gonna be, a bit weird, like two solids. So no, we don't want that. So that's why we need to do 0 to pi. It's important to consider this. So we are lucky that we have a symmetry here. And so now let's copy this and evaluate the other examples. I didn't expect it to be this long. Okay, so let's copy this. And let's go here. Now we paste here, okay. Now let's go to example 2. So example 2, it's basically, he wants us to convert this integral, x squared plus y squared, into square root of x squared plus y squared, from 0 to 1 minus y squared, and here from negative 1 to 1, x, y, z, dz, dx, dy. Okay, we want us to convert it into cylindrical, and that's gonna be not too hard. Should not be hard. Okay, so first we do have we know that x equals r cosine theta, y equals r sine theta, and z is z. Now we can use that. We know also r squared equals x squared plus y squared. Now here, let's just do the integral, and then we do the boundaries. So r cosine theta times r sine theta times z remains constant, so dz, and then we should do, as we'll see, we should start with z, okay, and then go dr d theta or d theta dr, it's fine. So dz, say dr d theta, okay. Now for the z, we just convert, we know that r squared equals x squared, so we're gonna have r squared, okay, r squared, they are no numbers, just, yeah, it's r squared, and then we're gonna go also, here we're gonna have r, so from r squared to r, so the square root of x squared plus y squared is r, and for the y, we're gonna go from 0 up to 1 minus square root of 1 minus y squared. Now this is basically x squared, okay, so we have x squared plus y squared equals to 1. Now the radius is 1, r equals 1, and so it's gonna go from 0 to 1, so r squared equals 1, and that's for our r. So we found z. Now we go to r. Now if we want to draw this, it's gonna be a bit complicated. I don't want to do it. And yeah, for the thetas, it's gonna guess, yeah. Okay, let's draw it. We need to draw it. And so this is basically z equals x squared plus y squared. This is a paraboloid, and then we have z equals square root of x squared plus y squared. Taking a different type of paraboloid. Now this is our paraboloid. Now this is an xyz. Okay, and let's try to draw our paraboloid, the other paraboloid. So z equals square root of x squared plus y squared. Okay, so it's gonna be a cone. It's gonna be a cone. So this is basically a cone. So it's gonna be like this. Okay, and so we want the volume between the paraboloid and the cone. And so the lower part, that's why the lower part is the paraboloid and the upper part is just the cone. So it's gonna be something like this. And so here, it's gonna be something like this. And the volume is gonna be this part in between. And now, as you can see, you can draw some hidden lines to make this a bit more easier to understand. Okay, and the areas between is just the solid that we are going to evaluate. Now, as for the y, it's gonna be go to the xy plane. In the xy plane is gonna just have the circle with radius 1. X squared plus y squared equals to 1. Okay, and so r is gonna go from 0 to 1, and theta is gonna go from 0 to 2 pi. Now that's basically our converted triple integral. Let's take another example. Now, example 3, he wants us to write this as a triple integral in cylindrical coordinates, and he gave us some conditions for z. That's basically simple. So let's go example 3. So triple integral q f of r theta z dz dv, and then we have q. So xyz such that, so this means such that z is bigger than or equal square root of x squared plus y squared. So this is looks like a paraboloid, x squared plus y squared. No, actually this is a cone, and smaller than or equal square root, and that's another cone, but it's like in the other direction. So 8 is x squared minus y squared. So these are cones. If you have the square root, it's gonna be a cone, so z is gonna be squared. So now let's basically do this in cylindrical coordinates. So f of r theta z dz dr d theta. Now for the z, we have z equals, so z is from x squared plus y squared. Now let's draw this. So we're gonna have two cones. One cone is the upward direction, so like this, and the other is in the downward direction, but it starts at z equals 8, so it's something like this. And we want this area in between, so it's something like this. Okay, and we want this volume, this volume, it's a solid. Okay, so we want this solid in between. So the graph that's at the bottom is just the square root of x squared plus y squared, and the one at the top is just z equals 8 minus x squared minus y squared. And so we want to start with the one at the bottom, so x squared plus y squared. So we have 8 minus x squared minus y squared. Now this is for the z. Now in order to find the r's, now let's draw this in 2D. So let's draw it as xy. So in the xy, if we equate the two equations, if we equate z's, so we're gonna have z equal, yeah. So if we equate the bound, sorry, if we equate the two equations, so x squared, yeah, we want to find the function in the xy plane, so x squared plus y squared, it's gonna give us 8 minus x squared minus y squared, okay, and square both, we're gonna get x plus y squared equals 8 minus x squared minus y squared. That's basically gonna give us something like no, it's gonna give us 2. It's not gonna cancel, it's gonna give us 2. So 2x squared is 2y squared. That's basically a circle. That's a circle with radius 2. Square root of 4 is 2. Now x squared plus y squared equals to 4. Now, so the radius is gonna be just from 0 to 2. Now for theta is gonna be from 0 to 2 pi, and that's basically our triple integral. That's simple. Okay, let's see other examples, or if we have anything else that we can go through. Now these are our examples that we solved. Now, okay, yeah, so we're gonna now cover the spherical coordinates. So let's cover the spherical coordinates. Now, what are the spherical coordinates? So the spherical coordinates, phi, rho, phi, theta, have a relationship with x, y, z, and also r. So theta is just, as we defined it in cylindrical coordinates, just the angle between the x-plane and the projection of r here in the xy plane. Now let's go to the new angles, which are phi. Now phi is basically, if we draw a line here up to the point that we are considering, okay, the point in spherical coordinates, if we draw a line, this line is gonna represent basically it's gonna represent the distance from the origin up to this point, and the angle between the z-axis, and this line is just gonna call it phi. Okay, and then we have rho. What is rho? Rho basically is the distance between the origin and our point. So phi is the angle between that distance, between that line or that vector, or whatever you call it, and the z-axis. And so this is our definition of the spherical coordinates. And now there are some relationships here, as you can see. Z equals phi cosine to, or rho cosine to phi. This is rho. Okay, rho cosine to phi. It's basically obvious. You can see that Z is just, you have rho and you have this. And basically, since this is the angle that is, we want to find this adjacent distance, and this angle is between the hypotenuse and the adjacent line, so it's gonna be just z equals to rho, so z is gonna equal to rho cosine of phi. Okay, and if we want to find the x and y, we're gonna now look at how we're gonna find those. So there is a relationship, it's simple. Okay, basically we want to find this line. Okay, so this line is basically gonna be the opposite, so this line is basically also this line, which is also the opposite line. So the opposite line, and this is the hypotenuse, is gonna be the xy line, this line, or r, is gonna be basically rho sine of phi. Now, how can we relate r to x and y? If we know the angle theta, we can basically find x and y by doing r. X equals, we know that x equals cosine theta, and now we do have r, so x is gonna equal to r, and r is phi sine, or rho sine phi, times cosine theta. Now this is y. Now for the y, this is x. For the y, we have r sine theta, so y equals the r, the same r, rho sine phi, times sine theta. And now that's basically our x and y coordinates, and that's easy. With that we can convert from cylindrical to spherical, from spherical up to rectangular coordinates, and also we can convert to spherical coordinates easily. So we can relate r and you know, this is r, and theta is just, we can find a way to find theta. Okay, we gonna need to find theta. We're gonna now see how can we find theta here. Okay, so that's basically it. Yeah. So now let's see the definition of spherical coordinates. So spherical coordinates represent a point P in space as an order triple rho phi theta, in which rho is the distance from P to the origin, so that's the distance, and phi is the angle OP that makes for the positive x-axis, so the angle between the line. OP is just the distance from our origin up to point P. So this is the origin, this is point P, and this is the vector OP, okay? And phi is just the angle between the vector OP and the z-axis. And so phi should be, of course, bigger than 0 and not more than pi, which is 180 degrees. Cannot be more than 180 degrees. And so, and the third condition is just theta is the angle from the cylindrical coordinates, which is from 0 to 2 pi. Okay, and so these are different, you know, different coordinate constant or constant coordinate equations in spherical coordinates. They could yield spheres, single cones, and half planes. Okay, and so let's discuss why that. So we have phi equals phi naught, in which rho and theta can vary. Okay, so when we have phi, when we let phi be constant, so we're gonna get r, sorry, we're gonna get rho phi theta. Okay, and that's gonna yield us a cone. It's gonna yield us a cone when phi is constant. So phi naught, phi equals phi naught. It's gonna yield us a cone. Why is that? So let's say that the angle between our vector and the z-axis is just constant. Well then, and p can vary. So p can be this, and can be any length. So p can be any length, and also theta can vary. So theta can, we can have a line like this. We can have also a line like this with different thetas. Okay, a line like this, but with, of course, constant phi. So this, the combination of this, of all of these lines, is gonna yield us basically a cone. That's basically what happens when we let phi be a constant. Now, if we let, now this is the point, of course. Now, if we let rho be a constant, so say and vary phi and theta, so say rho equals rho naught, then we have rho naught phi theta. Now this is gonna yield us a sphere. It's gonna yield us a sphere. Why is that? Well, basically, if we have a constant phi, we cannot change phi, okay? So we have only specific values for phi, okay, a specific value. But we can vary phi and we can vary theta, so theta can be like this, and this with varying theta, and but also we can have this vector, okay, with the same rho, but with different phi's and different thetas. Well, the combination of these lines is gonna yield us basically what we see here is sphere in the cyan color. And now if we have theta equals theta naught, if we let theta be a constant, so we have rho phi theta. Now this is gonna yield us a half plane. Now why not a full plane with us? Let's see. Let's see why is that. So we have theta equals theta naught. We have rho and phi. So yeah, so theta equal to theta naught. When we have a constant theta, we cannot change it. So we can only have lines along this axis, along this, plane. However, when we can't change phi, so we can have something like this. We can have a line like this. Or as you can see, yeah, we can have a line like this. A line like this, but we cannot change phi, a line like this. And the reason why we have a half plane, and so, yeah, so, and we vary also rho, we can have longer lines. So, and this combination yields us a plane or half a plane. And the reason we cannot have a full plane is that we said that phi is always between 0 and 180, or pi, or 180. And phi, so phi cannot be more than 180, and that's why we get a half plane and not a full plane. Phi only can be from 0 to pi, and that's it. Now here we have, okay, so we covered that. Yeah, so here we have the equations relating spherical coordinates to Cartesian and cylindrical coordinates. So first we have r equals phi psi theta, and we showed you why is that. We have also x equals r cosine theta, and basically r we said also is rho sine phi, so x gives us this, y gives us this, and then z is just rho, so here z is rho cosine phi. Okay, and we discussed why is that, and then just basically rho is the square root of x squared plus y squared plus z squared, so that's basically the distance formula. Okay, so the distance from the origin, the point distance formula. And then we know that x squared plus y squared is r squared, so it's just r squared plus z squared, so we can convert also to cylindrical coordinates. Now, let's do some examples. So we have here, we want to convert from cylindrical to rectangular, okay, or from spherical to rectangular, so we want to find x, so x is basically rho, so 4, and then it's just, of course, cosine theta, so cosine pi over 4 times cosine, is it cosine or sine? Cosine, I think it's cosine pi over 6. Okay, so it's a sine phi, sine of pi over 6. Now this will give us x equals to 4 cosine of pi over 4. So pi over 4 is 45 degrees over 6. Now root 2. As for the y, we're gonna have 4 sine of pi over 4, sine theta, and then sine of pi over 6, so sine phi, which is 4 sine of pi over 4, sine of pi over 6. That's basically y equals to root 2. And as for the z, it's just phi cosine of, or rho cosine of theta, so 4 cosine of rho, okay, of rho, which is pi over 4, or pi over 6. So 4 cosine of pi over 6, which is z equals to 2 root 3. And our coordinate is just root 2, 2 root 3. Okay, so let's go to example 2. Now we want to convert this cylindrical coordinates into spherical coordinates. So we will have first phi, so we know that r equals, okay, yeah, so we know that r equals rho cosine theta. Is that right? Or rho cosine phi. And r is also equal rho sine phi. Sorry for this. So r equals rho sine phi, and z is equal to rho sine phi. Okay. Okay. So first, let's find rho. We can easily find rho by using this formula, r squared plus z squared, and we have r and z, so rho is gonna be basically the square root of 2 squared plus minus 2 squared, which is 2 root 2. Now since we find rho, we can easily find r and z. So z is gonna be, so r equals rho sine of phi. Now we do not have phi, we have theta. And so since we have theta, we might need to convert first to rectangular coordinates, and from rectangular coordinates we can convert to spherical coordinates. So if we want rectangular coordinates, we're gonna get x equals r cosine theta. So x is gonna equal to 2 cosine of 2 pi over 3, which is -1, and y equal to r sine theta, which is 2 sine of 2 pi over 3, which is basically gonna be 0. Oh, sorry, root 3. Y equals root 3. And now since we have the y, and we have the x, we have theta, we have rho, we can find phi. We have the rho. Yeah, we have the rho. Do we have r? Yes, we do have r. Actually, we could find phi. We do not need to do this. We can use the formula r equals, so let's find z first. Now z equals, yeah, we can use the formula r equals to phi sine, rho sine phi. Okay. So we have rho and we have phi, so sine of phi, or phi is basically sine inverse of r over phi, over rho. And now phi is just sine inverse of r, which is 2, over rho, which we found to be 2 root 2, which gives us pi over 4. Now this is our phi. We have our rho. Now we need the z. Z is just r sine of phi. Now since we find phi, there's cosine. Cosine of phi, then z is gonna be just 2 cosine of pi over 4. Love it, root 2. Now our coordinates is just 2 root 2, pi over 4, and root 2. That's basically our spherical coordinates. Now example 3, he wants us to convert rho secant phi into rectangular, and we know that rho is just the square root of x squared plus y squared plus z squared equal to secant theta. Now secant theta, what is secant theta? Well, secant theta is just 1 over cosine, and if you want to get secant phi, sorry. So yeah, and we know that cosine phi is just from here z over rho. So z over rho is cosine phi, so secant phi just rho over z. Okay, and now secant phi is just rho over z, and we know that rho is just x squared plus y squared plus z squared over z. Now we converted this, basically. Yeah, we did convert this. Now I think we can cancel some things. So now secant phi is just, we said, yeah, xy squared. Yeah, so secant phi z over rho, cosine phi z over rho, which is rho over z. So, and then we can cancel these, so we get, yeah, so we get 1 equals 1 over z, or z equals 1. So we converted this into rectangular coordinates, so this equation basically rho equals secant of phi, just z, just the plane z equals 1, which is interesting. And now we'll say example 4, he wants us to convert this into spherical coordinates, which should not be very hard. Now let's do this. Okay, so let's say that first rho squared minus 4. So now that this is rho squared, and minus 4, z is just rho cosine phi equal to 0. That's our spherical equation. It's very interesting. Now this is our sphere. Say this is an example: x squared plus y squared minus equals plus z minus 1 squared. So rho equals 2 cosine theta, 2 cosine phi. It's an example 3. Okay, no, not this example. So I think he's talking about example 4, which is a sphere, yes. So he's talking about example 4, and this is the sphere in example 4. Or it's a different example. Yes, a different example. Here's a different example. Here we have rho equals 2 cosine phi. Now if we convert this into rectangular, it's just gonna be square root of x squared plus y squared plus z squared equals 2, and we said cosine phi is just z over rho. This is different than secant phi. Secant phi is rho over z, so this is z over rho, and then rho is just square root of x squared plus y squared plus z squared, and then we get x squared plus y squared plus z squared equals to 2z. And if we take this to the other side and complete the square, we're gonna get this. So z, okay, 2 over 2, all squared is minus 1, all squared equals 2. Yeah, so we're gonna add 1, 1. That's our sphere. So that's a different example, but similar to our example 4. Yes, similar. And so this can be also simplified. Let's notice this can be simplified to rho minus 4 cosine phi, so equals 0, so rho equals 4 cosine phi. This can be even further simplified. Okay, which is very similar to what we see here. This is just the difference is that the radius of the sphere here is 4 and here is 2. Now this is a cone, so anything that has z equals square root of x squared plus y squared is a cone, or z squared equals squared plus y squared. We have phi equals pi over 4, and yeah, pi equals pi over 4. So this is the phi, and this is the cone that we had in some of the examples. And now, yeah, so the volume, differential, and spherical coordinates. Okay, so this is important. The volume differential in spherical coordinates, so dv equals rho squared sine of phi, d rho, d phi, d theta. Now we do have this. It has a whole explanation, but I think I can stick with the differential. Okay, differential way. Now it's basically multiplying phi 2 times. Okay, so first we have phi sine theta, and we have phi sine theta delta theta. Okay, which is the change in theta. It's just the arc length. Okay, so and he's also multiplying rho sine theta, which is this part, in order to get this whole big thing here. So this is rho sine theta, sine phi delta theta, this is arc length, and we're also multiplying by delta p here in order to get the depth, and we are multiplying by rho sine theta, which is this rho sine phi, multiplying this all together to get this partition of our sphere, which is here. D rho times rho d phi times rho sine phi d theta. So it's very interesting to, square sine phi d rho d phi d theta. This is our sphere. This is our cone. Pi over 3, rho equals 1. Ice cream cone, example 5, yeah. And these are the conversion formulas, okay? So if you want to take a look at them, try to memorize them. since we will need them a lot in our spherical and cylindrical coordinates. So yeah, maybe you can solve an example or two. Let's try to solve an example. Yeah, okay, so let's take these. Try to solve some examples here. So this. Okay, so he wants us to evaluate this integral, for example 1. Have this integral 16z dv, and then we have e. So we have x squared plus y squared plus z squared equal to 1, and this is basically a sphere, but we want only the upper half of the sphere. So this sphere, we want this upper half. And so the way to do this is just, we're gonna use the spherical coordinates. Okay, that's not a sphere. Okay, so it's something like this, yes, okay. X, Y, Z. Okay, so let's now do this. Let's do 16z. And then dv we said is just rho squared sine phi dp rho squared sine phi. We could also convert z. So d rho d phi d theta. D rho d phi d theta. So 16z. It's interesting. This, and this. 16 now z, if we want to convert it into our coordinates, so rho cosine, sine or cosine. Start to forget this now. So z, let's go to our here. Z is just rho cosine phi. Cosine phi. Okay, so it's gonna be just rho cosine phi. Now as for rho is just gonna be 1 since our radius is 1. So it's gonna go from 0 to 1. Yeah. Or no, actually, yeah. Since here we have rho squared equals to 1, so rho equals to 1. Plus minus 1, we get 1. So from 0 to 1, it's gonna go like this. And now we have also the d phi. Now for phi is gonna go from, so let's imagine this. It's our phi. Okay. We know that phi is from bigger than 0 and bigger than pi. So it should be bigger than 0 and bigger than pi. Okay. And so let's see how can we approach this. Okay. Now we do have this for cosine phi. Okay. Okay, so phi can go from 0 to pi, but we won't have a sphere, so we're gonna go from 0 to pi over 4, over 2. So we get half a sphere. Now for theta, or actually we can approach it in two ways. But if we want the upper half of this, so we're gonna go like, let's see. Okay, let's see how can we do this the best way possible. Yeah. I think the best way to approach this is just to say 0 to pi over 2, and then you go from 0 to 2 pi. Mhm. Okay, so I think that's the way to go about it. So we're gonna get only a half square, a half sphere. To get a full sphere, we can just say rho equals c. Spherical wedge. It's interesting. Yeah, I think we have done it the right way. I think we have done it the right way. From 0 to 2 pi. And now that's basically it. So example 2. Example 2 is gonna show us more about this. So let's go like this. Now the example is just x squared plus y squared plus z squared. This is rho. And we have dz dx dy goes from 0 to so square root of x squared plus y squared, and also from square root of 18 minus x squared minus y squared. It goes from 0 to 9 minus from 0 to 3. Now this goes rho dz. Yeah, so now the dv that we have just gonna be rho squared sine of phi d rho d phi d theta of triple integral. Now for this we're gonna have, so for this we're gonna have z equals to x squared plus y squared. Now if we want to convert from this into polar and we want to find the phi, let's just try to draw this. Now we know this is a sphere, so so phi squared, rho squared. Now this, and this is just gonna be a sphere. Okay, it's gonna be basically a sphere here. And it goes here in the xy plane, it goes from square root of x squared plus y squared to up to, yeah, so this is first a paraboloid, so like this, but also the other one is just 18, so square root of 18 here. So basically that's the volume. Okay, okay, so that's our volume here. And the xy is just we let this, yeah, so if we want to get to the xy, you just equate the two z's, x squared plus y squared, the two ends here, so this and this, equal to square root of 18 minus x squared minus y squared. This looks like a circle, x squared plus y squared equals to 18 minus x squared plus y squared. So x squared, so 2 plus 2y squared equals to 18, and so squared plus y squared equals to 9. And so this is a circle of radius 3. Now, as for phi, we need to find phi. So we're gonna use this z equals square root of x squared. Let's just say x squared plus y squared, and then yeah, take z squared. Now we know that z is just rho cosine of phi, and x is just O squared, of course. Sine squared, so phi squared, now cosine of, or no, sine of phi cosine theta plus rho squared sine of phi all squared sine of theta squared. Now we are not going to get a phi here, we're gonna get something like a relationship between phi and cosine and theta, phi and theta, plus cancel these, sine squared phi, sine squared theta. This is interesting. We can get, yes, we can get something like tan squared of phi. Now we take this as common factor. It's gonna equal to 1. And so tan phi is gonna equal to pi over 2. So tan inverse of pi over 4. Pi over 4. Or theta is gonna be y over 4. So we said tan theta is just, tan phi is 1. So basically this is sine squared of phi cosine theta squared plus sine squared theta. And so we'll have 1 phi equal to pi over 4. And that's our phi. So for the phi, we found our phi. It's from 0 to pi over 4. And for our theta, I think it's 0 to 2 pi. Now our phi, I need to find phi. So it's basically going to go from 0. It's going to go up to a specific point. Now let's try to find phi. Now phi can be found in different ways. Can we use this? So we have x equals square root of 9 minus y squared, so x squared equals 9 minus y squared. So we're gonna have phi sine of, yeah, sine of phi cosine of theta all squared. So rho squared sine squared cosine squared equals 9 minus rho sine squared phi sine squared theta. Now this all squared, if we take some common factors, so squared, okay, and so yeah, sine squared phi also. Cosine squared theta minus sine squared theta. This looks like an identity. And now we need to find theta. So theta we said is from 0 to 2 pi. So if we say 2 pi, so cosine squared of 2 pi is 1. And sine of 2 pi is 0. So we get phi squared sine of phi equals 9. Okay, and so we have phi equals first side squared equals to 9 to 3 secant phi, and that's, so rho is 3 secant phi, so it goes from 0 to 3 secant phi, and here from 0 to pi over 2, 0 to 2 pi, and that's basically our volume in spherical coordinates. Yeah, we found it from this 9 minus phi squared. It's interesting, I like it. I love it. I really love it, and I think it's actually we could have gotten this also from, if we try to do the upper part, the upper boundary of z. So z equal to, yeah, so z equals square root of 18 minus x squared minus y squared. I think we could have gotten the same answer. Now z is just, so z squared equals 18 minus x squared minus y squared. Now z is just rho cosine of phi all squared equals 18 minus rho sine of phi cosine of theta all squared minus rho sine squared of phi sine squared of theta. And now this is basically, yeah, so basically I can just do, I can take here rho squared cosine squared of phi plus rho squared sine squared of phi. Okay, I think we're gonna have our cancellations here, yeah. Okay, so cosine squared of theta plus rho squared sine squared of phi plus sine squared theta equals to 18. And here we can take common factor, so we're gonna have rho squared sine phi. Now here also we can take a common factor, so equals 18. Now we're gonna have rho squared equals to 18, or rho equals square root of 18. I don't think this is correct. Or rho equals 3 root 2. Rho is not constant here, we do not have a sphere really. Okay. And so I think the most accurate one is this, rho equals 3 secant phi. And then this is our volume. And so thank you for watching. I hope you benefited from this.